All right, we're going to be talking about quadratic regressions. Just like we did when we did linear regressions, we're going to use the data and stats page in your calculator. So here in your notes, I've listed the steps for the Nspire, what we do. So first we're going to enter all of the data into a list and spreadsheets page. And then we're going to add a data and stats page, and it's going to plot our data after we label the X and Y axis. And then we can get the equation by doing a regression. So let's do one of these problems together. So example 1 says the table shows the run times in seconds a certain computer program requires to analyze the given megabytes of data. So first we have our data in megabytes. I'm going to label this as my X value. And we have our run times in seconds. That's going to be the Y value. So first it says find a quadratic function in the form f of x is equal to ax squared plus bx plus c that provides a reasonable fit to this data. So that is the standard form for a quadratic. So we're going to do a quadratic regression is what that's telling us. Even though here all of our data is increasing, that's showing that at some point it's going to decrease, either later or before when our data is negative, which would not apply for any of our answers. But let's find out when that happens. So I'm going to open a new document. We're going to add a lists and spreadsheets page. I'm going to make this so that we can see both pages at the same time. Here we go. That's a little better. So in my calculator, I'm going to label the X and the Y columns. And first I'm going to enter my data. So we have 1 megabyte, 2, 3 megabytes, 4 megabytes, and 5 megabytes. Then my run times, I have 1.3 seconds, 3.3 seconds, 6.7 seconds, 10.7 seconds, and 16 seconds. Now right here is where most people make a mistake. See that last cell that I'm in with the 16? If you don't hit enter, your calculator is not reading anything in that cell. So be sure you hit enter before you add another page. So here at the top it says our next set of directions we're going to, so we just did the list and spreadsheets page. So let's add a data and stats page. So you do that by Control Doc, you'll add a page, and add a data and stats page. So here we're going to change the bottom axis to our x-axis and the left axis to our y-axis. That looks like part of a parabola. So it looks like our data is just, our runtimes are just going to increase. So it would decrease over here and we'd have our vertex somewhere over here in the graph. But that's fine. So now the question is, what is the equation for this reason, for this data given? So we're going to go to Menu, Analyze, Regression. I'm going to go to Show Quadratic. That's number 4. And there's our equation. So I'm going to go ahead and round everything to 2 decimal places. So here my equation is going to be y equals 0.51 x squared plus 5 plus 0.59x plus 0.16. So here you have that A, B, and C value. Part B asks us to use that equation to estimate the runtime, it would need to analyze 3.5 megabytes of data. So remember the megabytes of data, that's your x value. So what we're going to do is I'm going to say y equals 0.51 times, and here we want to replace our x with 3.5 squared plus 0.59. Again, we're going to replace with 3.5 megabytes plus 0.16, and then we can just evaluate. So our runtime, y, equals, and here I'm just going to add a calculator page, and we can type that in. So I have 0.51, 0.51 times 3.5 squared plus 0.59 times 3.5. You can put your 3.5 in parentheses if you'd like, plus 0.16. And I get about 8.5 seconds. So my answer would be 8.5 seconds. So C, again, we're going to do the same thing, only this time I want to know what's going to happen for 10 megabytes of data. I'm going to use my same equation that we found when we did our regression. So I'm going to use y equals 0.51 times, this time we're going to use 10 squared, plus 0.59 times 10 plus 0.16. So I'm going to evaluate 0.51 times 10 squared plus 0.59 times 10 plus 0.16. I get 57.06 seconds. So my answer is 57.06 seconds. So almost an entire minute to analyze 10 megabytes of data. Example 2. Example 2 says Amory recorded the distance and height of a basketball when shooting a free throw. So we're going to find the quadratic equation for this relationship of the horizontal distance and the height of the ball, and it says here to round to 3 decimal places. So here in my table I'm given x is my distance in feet, f of x, or y, remember f of x is y, is also my height in feet. So I'm going to go ahead and start a new document. We're going to start with the List and Spreadsheets page. The first thing I want to do is label my columns x and y. And I'm going to list all of my distances for x. So I have 0, 2, 6, 9, 12, 13, and 15. And then all of the distances that correspond in height. So I have 4, 8.4, 12.1, 14.2, 13.2, 10.5, and 9.8. And again, remember to hit enter after that last cell. Otherwise, your next table will not include that point. Sorry, your next page, not next table. I'm going to add a data and stats page. And it just kind of throws all of my points here. I'm going to organize them by labeling this the x-axis and then the y-axis. There's our table. Looks like there's a point that's off a little bit there, but if I hover, I can check. No, 13 and 10.5 is a point. 12 and 13.2 is a point. 15 and 9.8 is a point. So in the real world, not all data will be really nice and exactly on the line. That's why we're doing a regression, because we want to know what's the average, what's the best fit for a regression here. So we're going to go to Menu, Analyze, Regression, and we're looking at quadratics. And we can see here, before I do that, that this does look like a parabola about. It looks like a parabola that's facing down, one of the sad, frowny face parabolas. So we're going to Menu, Analyze, Regression, Show Quadratic. Here's our quadratic, and the problem says to round to 3 decimal places. So let's go ahead and do that. So my equation is y equals, and I've got negative, which makes sense because we're facing down, 0.1179. So that 9 is going to round that 7 up to an 8. So 118 x squared plus 2.1124, so that's going to stay at 2, x plus 4.2150, so the 5 stays at 5. 1, 2, 1, 5. Part B says use this function to approximate the maximum height of the ball. So there's a couple of ways we can do this. I can find this by hand by using the axis of symmetry and plugging that back in, or I could graph this in a calculator, and I happen to have this calculator here, so why not? Because it's going to be a decimal, I can see all these decimals, it's not going to be a very nice number, so let's go ahead and use a calculator. So I'm going to Control Doc, add a graphs page. We're going to graph that y equals, so we've already got f1 of x equals, so I'm going to do negative 0.118 x squared plus 2.112 x plus 4.215. So here are my y values. In my table, I saw that I got up to right around 14, so let's change this here to a 15. And then our distance here, we had 15. Let's go ahead and change this. Let's see if 20 works pretty well. So to find my maximum, remember we can analyze, so Menu, Analyze Graph. And my maximum, because it's at the top, we have a maximum point here at 8.95 and 13.7. So 8.95 is the horizontal distance. 13.7 is about the highest that basketball will be. So we have 13.7 feet. Example 3. Example 3 says this table shows the population of a city every 10 years since the year 1970. So here, and this is important to read, we have our years since 1970. So if it's at 0 years, that's the year 1970. 10 years, 10 years after 1970. So this is 1970. So I'm just going to make a note. 10 years after 1970, that's 1980. 20 years after 1970, since 1990. 30 years since 1970 is the year 2000. And 40 years after 1970 is the year 2010. Now this is where in a table sometimes you can get very lost because the population, notice it says in thousands. So here, this is not 489 people, it's 489,000 people. So when we enter this into our table, we're going to use these numbers. But when we get a result, we're going to be sure that we add the 1,000. And I'll show you how to do that in just a minute. So here, A says find the best fitting quadratic model for this data. And again, it asks us to round to 3 decimal places. So let's go ahead and add a new document. No, we don't want to save. I'm going to add a list in spreadsheets page. Again, we're going to have X and Y. So X, we have 0, 10, 20, 30, 40. In my populations, we have 489,000, remember, 801,000. This is where it gets interesting, because we have 1,202,000. We'll talk about how that works in a minute. 1,998, 2,959. Again, remember, be sure you enter that last data point, otherwise it won't be included on your data and stats page. So I'm going to add my data and statistics page. And again, it just kind of throws our numbers in here. So let's say the horizontal axis is X, the vertical axis is Y. And that looks pretty parabolic. It looks like it would go up over here, but that would be a negative time, so we don't even look at those. So to answer A, let's see here, analyze regression, show quadratic. There we go. Let's go ahead and write down that point. Remember, we're going to round to 3 decimal places. So I've got Y equals 1.20, this was 92, so it stays a 9, x squared, plus 12.9986, and that 6 rounds that 8 up to a 9, x, plus 504.257. Part B says using this model, this is our model, what will be the estimated population in the year 2020? Well, remember here how we started? Zoom in and take a look here. We said 0 years was 1970, 10 years was 1980, 20 years was 1990. So if we got down to the year 2020, that would be 10 more years. So that would be 50 years since 1970. So what we're going to do is that's our x value. Ooh, there we go. So I'm going to plug in that x value. So I've got y equals, so our population, of course in thousands, we'll talk about that again in a second. We're going to plug in for x, so I've got 1.209 times 50 squared plus 12.999 times 50 plus 504.257. Again, I could solve this by hand. That's a lot of decimals though. We are going to get a decimal, and that's fine. So let's go ahead and add a calculator page and evaluate. So I have 1.209 times 50 squared plus 12.999 times 50 plus 504.257. And that gives me y equals 4,176.71 people. Well, remember here we said it was our population in thousands. So if I added 3 zeros, that would give me my population. So we're technically multiplying by 1,000. So again, 1,000. So that 1,202,000 is actually 1,202,000. Again, so we're just adding the zero. So here, I could say my population would be, well, let's go ahead and take this because you can't have a fraction of a person. I'm going to round it up. So we've got y equals 4,177. And if I just add on, we'd have 4,177,000 people.